Welcome to Unit 4. Here we're going to be looking at radical expressions and equations. So we'll get started by looking at some of the properties of radical expressions and how to simplify them. Let's get started. Okay, so here are the parts of a radical expression. This whole thing is a radical expression. This is the index. This is called the radicand. And this symbol here is the radical symbol. So what you're going to go through is 1 through 6. Go ahead and put the equivalent statement here to the right, and then use these to answer questions 7 and 8. And then we'll go ahead and take a look at it together. Alright, so hopefully this was pretty simple. Here I'm squaring 4, and that's going to be 16. And here I'm finding the square root of 16, which is 4. Here I'm cubing 2, and that is 8. And here I'm finding the cube root of 8, which is 2. Here I'm raising 5 to the 4th power, and here I'm finding the 4th root of 625, which is 5. So based on this, we should be able to identify exactly what the index in a radical expression indicates. Here we are taking the square root of 16, which means that we are looking for a number, the root, that I can multiply by itself 2 times to get 16. Since here I'm looking for the cube, or the 3rd root of 8, that means I'm looking for a number that I can multiply by itself 3 times to equal my radicand. And since here I'm looking for the 4th root of 625, I'm looking for a number that I can multiply by itself 4 times to equal the radicand. So that's exactly what the index is indicating. How many times must I multiply that root in order to equal my radicand? And of course, the invisible index that we have on the normal square root symbol is 2. So even though we generally don't write it there, we really have a 2 here. So if you see a radical symbol with no index, that means that we're looking for the square root of whatever the radicand happens to be. Alright, so hopefully you have this copied down nice and clear. If not, go ahead and copy it down now. And let's take a look at some of the key points dealing with radical expressions. The index indicates how many times the root must be multiplied by itself to equal the radicand. That's what we just discussed. So in this situation here, since it's the 3rd root of 27, the index is indicating that we're looking for a root that we can multiply by itself 3 times to get 27, which is of course 3. In general, if we have b to the n is equal to a, what we're saying is that b is the nth root of a. So let me give you a little example here. I might say that 3 squared is equal to 9. And what that means is that 3 is the 2nd root of 9. I could also say 9 squared equals 81. And that would be saying that 9 is the 2nd root of 81. To kick it up a notch, I could take 5 to the 3rd power. That's 125. And here I would be saying that 5 is the 3rd root of 125. Alright, so now we have the great linkage between a radical expression and an exponent. And we saw that in the discovery problem, right? The 4 squared is 16, the square root of 16 is 4. There's clearly an inverse relationship there. In fact, a radical expression is just another way of writing an exponent. And so this is the way that it works in general, and we'll do a couple examples here in a second. And in fact, in class, we'll prove why this has to be true. So if I am taking the square root of some number a, or at some variable a, to the nth power, and I'm taking the mth root, I know there's a lot of variables here, it'll make sense in a second, then I can rewrite this as a to the n over m power. So let's take a look at a simple example. Here I have the 3rd root of 27. So I have 27, and since the exponent here is a 1, it will be 27 to the 1 over 3, or 27 to the 1/3. And so I know how to find the 3rd root of 27, that's 3, and that means that 27 to the 1/3 is also equal to 3. All right, let's take a look at a slightly more complex situation. All right, so here I am taking the fourth root of x to the third power. And so going back and reminding myself of how I can rewrite these expressions, I will have x to the 3 over 4 as one exponent, just like that, x to the 3/4. Okay? Those are equivalent expressions. So that means that whenever I have a radical expression, I can always rewrite it as an exponent expression like this. And the most common time that we'll see this is when we have some value, either a variable or a number, and it's being, we're taking the nth root, the third, fourth, fifth root. We can just rewrite it as that value to the 1 over 3 or the 1 over 4 or whatever it is. All right. Now, another very powerful tool is that we can simplify these expressions by distributing the exponent, or radical, to both the coefficient and the variable, and then evaluating. Or in other words, we can distribute a radical or an exponent to all the pieces that it is being applied to. I'll show you exactly what that means here. So here we have this expression. It's the square root of 25 times x squared. Now, let's rewrite this as an expression with an exponent instead of a radical. So why don't you try that using what we just discussed in the second key point here. All right, so inside we have 25x squared. That's our radicand. And since this is all being raised to the first power, we can take 25x squared and we can raise it to the 1 over 2. Remember, there's an invisible 2 here. So we can rewrite this as 25 to the 1/2. And now what this property is saying is, since we're taking 25x squared, all of it, and raising it to the 1/2, then we can raise each piece independently to the 1/2 power and then multiply them. So we can rewrite this as 25 to the 1/2 times x squared to the 1/2. And this allows us to simplify even further, because 25 to the 1/2 is just the square root of 25, as we discussed previously up here. And so the square root of 25 is 5. And here we have x squared to the 1/2. And if you recall, when I take a power and I raise it to another power, I am just multiplying the two powers together, and I will end up with x to the 2 times 1/2, or just x to the 1. All right, now let's do this again, but instead of rewriting our radical expression as an exponent first, let's just distribute the radical expression to both 25 and x squared. So we can basically say, okay, we have the square root of this whole thing. We can also take the square root of 25 times the square root of x squared. Notice this will only work if we have multiplication going on here. So if this were addition, it wouldn't work. And you might want to note that down. Addition or subtraction will not work. So what I'll have is the square root of 25 times the square root of x squared. And we can simplify further, of course, because we know the square root of 25, which is 5. And using the nice tool that we have from the previous key point, we can rewrite this expression as x to the 2 over 2. And 2 over 2 is just 1, so we just have x to the 1, or 5x. Same thing that we got previously. So it would be important to remember these key points. We will use them over and over again, and when we start actually looking at radical functions, we will want to make sure that we can simplify them so that we can understand what they're telling us about a real-world situation. Let's quickly take a look at some of the properties of exponents that you probably learned a long, long time ago and may or may not remember, just so that we're able to use them as we go forward. All right, so here are some simple properties. Notice they all require the first two, that the base is the same. If we are multiplying two expressions where the base is the same, then we are simply adding together the exponents. Imagine you had 2 to the 3rd times 2 to the 4th. You just have 2 times itself 7 times, and so you'd have 2 to the 7th. Here, if you have x to the n divided by x to the m, in other words, you're taking x to the nth power and dividing x to the mth power, then you're simply subtracting the two exponents. I'll give you a quick example here. You have 2 to the third over 2 squared. So when you write this all out, you'll have 2 times 2 times 2 over 2 times 2. Well, of course, 2 over 2 over 2 is 1 over 1, and so you're left with 2 to the first power. In other words, 3 minus 2, which is 1, or 2 to the first power. And if you have an exponent and you're raising it to another exponent, then you're simply multiplying the two exponents together. Quick example here, 2 to the third power to the second power. I'm just taking 2 to the third and multiplying it by itself. And of course, by the property number 1, we know that's just going to be 2 to the sixth. And of course, that's what you get when you multiply 3 and 2. So important to remember these as we go forward. We will definitely be using them to simplify some expressions. So now let's go ahead and actually put these to use. Okay, so let's try a couple out. We're going to try and simplify each expression so there is only one variable term and no radical symbols. So I want you to try both of these on your own. I know the first one looks daunting, but go back to your key points and remind yourself of all the things that you can do to get rid of the radical symbol and also to simplify these expressions, okay? So try each one on your own and we'll take a look together. Okay, so the first thing that I can do is I can simplify both the numerator and denominator here. I can rewrite each of these radical expressions with fractional exponents since I don't want any radical symbols. So my first step here is going to be to get rid of the radical symbols, and then I'm going to go ahead and try and combine the variables. So I'm going to have 512 x to the fourth. That's all to the first power. And so it's going to be all raised to the 1/3 divided by 8x squared all raised to the 1/3. Okay, now I can go ahead and apply this exponent to both parts of each of these expressions. So I'll have 512 to the 1/3 times x to the fourth to the 1/3. Now, when I'm taking x to the fourth and raising it to the 1/3, I can just multiply the two exponents together, so it's going to be to the 4/3. In the denominator, I will have 8 to the 1/3, and then x squared to the 1/3 is going to be x to the 2/3. This looks hairy right now, but it's about to get a lot simpler. You might not know this one off the top of your head, but it's a good one to remember here. 512 to the 1/3. This is, remember, the third root of 512. What can I multiply by itself 3 times to get 512? And if you try some numbers out, you'll find that 8 works. So this is actually 8. So I have 8x to the 4/3 over, and what's 8 to the 1/3? Well, what can I multiply by itself 3 times to get 8? The third root of 8, which is just 2x to the 2/3. All right, now we're in great shape because 8 divided by 2 is going to be 4. And we have two exponent expressions where the base is the same. So we can subtract the two exponents. 4/3 minus 2/3, that's nice and easy. We have a common denominator. 4 minus 2 is going to be 2, so it will be x to the 2/3. Certainly a lot of work, but a much simpler expression now than we had previously. All right, this second one here is a lot simpler in my opinion. We're only multiplying here. So remember, when we're multiplying, order doesn't matter. So we can go ahead and multiply 7 times 2 times x to the 1/3 times x to the 1/4. And 7 times 2 is simply 14. So we have 14x to the 1/3 times x to the 1/4. And if you remember the property where if we have two expressions with exponents and the bases are the same, we simply add the two exponents together. And 1/3 plus 1/4, I need a common denominator of 12, and that's going to end up giving me 7/12. You can do that to confirm on your own. So it'll be 14x to the 7/12. That will be my final expression. All right, I'm going to go ahead and give you two more to try on your own that we'll take a look at in class. All right, here are two more for you to try. Make sure that you write them without the radical symbols, simplified so that there's only one variable term. And you might be able to do some extra simplifying as well.